It's time to talk about our third data structure. And we're going to be talking about two types of linked lists in the next coming videos: singly and doubly linked lists. What problem did we encounter with arrays? Well, with static arrays, we only had a certain amount of data or memory that can be allocated next to each other in memory. But then both dynamic arrays and static arrays can increase their memory once it hits a certain limit and double up that memory in another location. But that operation every once in a while of doubling up the array in order to create more memory had a performance implication, and it cost us O of n. Additionally, arrays also had bad performance for any sort of operations like insert and delete that had to shift indexes over, especially when you inserted or deleted anywhere that wasn't the end of the array. And then came hash tables. They were great. We would pretty much store things wherever we wanted in memory, and hash tables would just take care of it for us and know where to place it in memory. We didn't have to worry about some problems that came with arrays. Life was good, but unfortunately, they weren't really ordered. So how can we solve this problem? Linked lists to the rescue. So does this mean we all should just be using linked lists all the time and disregard arrays and hash tables because linked lists are the best data structures? Nope. As always, there are trade-offs when it comes to data structures. So in the next coming videos, let's learn more about them so we can get a clearer picture. By the way, remember this diagram that I showed you in the hash tables videos? And I said that when we had a collision, one way to solve it was using something like this. And we had no idea what this data structure was. Well, this, John Smith to Sandra D, and this little arrow pointing, that's a linked list. So let's get started and learn what linked lists are. What is a linked list? As the name suggests, it's a list that is linked. All right, Andre, that's not very helpful. Can you actually explain it to us? All right, well, I have a little diagram here for you. A list, or in this case, as we'll find out soon, a singly linked list, contains a set of nodes. And think of nodes as these blocks. Both red and green block together is a node. These nodes have two elements: the value of the data you want to store, in this case, the number 5, and a pointer to the next node in line. So you can see the green block here points to the next node. The first node is called the head, and the last node is called the tail. Now, depending on some people like to call the tail anything that is after the head, so including this block over here. But I prefer the term tail referring to the very last node. Finally, linked lists are what we call null terminated, which signifies that it's the end of the list. So we know that this is the tail node because it points to null. There's nothing coming after it. Now, pointer is a term that you hear a lot in programming and computer science. And we have a video coming up discussing what a pointer actually is. But to focus just on linked lists for now, you can see that it's a very simple data structure. It's simply an element that links to the next element that links to the next element. And it keeps going until the last element that points to null. You can have them sorted, you can have them unsorted, and you can have nodes pretty much contain any sort of data type. But let's take a look at some pseudocode. Up until now, we learned how arrays work. And here I can just create a simple array, let's say a basket that contains our grocery list. We have apples, we have grapes, the most delicious of the fruits, and we have pears. Now, how can we have a basket that's not an array, but a linked list? Well, we can just say that our linked list, and this is not actual code, just pseudocode, I can say that our linked list will contain apples, that then points to grapes, that then points to pears. And these little arrows are essentially pointers saying apples to grapes to pears. Remember, this isn't actually code. I'm just creating a nice diagram for you. A more accurate diagram might be something like this, where we have apples in memory space of, let's say, A947, And this node points to the next node, which is grapes. That is at this location in memory. And then that node points to pears. That is at this location in memory. And because this is the end of the list, the tail, it points to null. Now, you're thinking to yourself, Andre, how come you're not just coding this in JavaScript? Just show us how linked lists work in JavaScript and stop with this pseudocode gibberish. Well, JavaScript doesn't actually come with linked lists built in. Remember what I said. Different languages have different tools available to them. Languages like Java have linked lists, while JavaScript doesn't come pre-built with linked lists. But luckily for us, we can build one. And this is what you typically do in programming. When you don't have something, you build it. And we have the building blocks to be able to build a linked list. And that's what we're going to do as part of an exercise coming up. But before we code our own linked list and create our own linked list data structure, let's do a fun little exercise. Welcome back. It's time for a little exercise. Why do you think linked lists may be better than hash tables or arrays, just from what we know right now? I want you to answer this question in your head or write it down before you go into the next video. I also want to show you a nifty little tool that I will link to in this video. And this little visual shows you how a linked list works. So you can play around with it and see where they might shine over arrays or hash tables. You see over here, we have a head with a value of 22 and a tail with a value of 89, and then other nodes connecting all of them. And you can use this website to do anything to a linked list. You can create, you can search, you can insert, you can remove. Let's do a insert here. I can either insert to the head if I click here, and if I click go, I enter the value 85. I can insert to the tail at the very end if I hit go. All right, that seems pretty simple, nothing too crazy. What if we insert somewhere in the middle? If I click over here and let's say at index of 2, I want to insert the value of 90, or let's increase that to 93. I hit go. Keep an eye on what's about to happen. Oh boy, what just happened? Don't worry, it looks a little bit complicated and we're actually going to code this all ourselves and build this in. But I want you to play around with this data structure and in your head come up with why we might want to use something like this. And in the next video, I'm going to tell you all about it so you can test whether your assumptions are correct. I'll see you in the next one. Bye-bye. Welcome back. I hope you are able to think about why linked lists might be good or bad. In this video, let's discuss the answer. One key thing that you may have seen is that linked lists have a sort of loose structure that allows you to insert a value into the middle of the list by simply resetting a few pointers, just like we saw in the animation. I can insert anything that I want, and the only changes that happen is somewhere in the middle here. And this is the same for deleting node in a linked list. And we remember with an array data structure how when we wanted to insert something that wasn't at the end of the array, we had to add the item, let's say in memory space 1, into here, and then shift all the items down and index it down, which cost us a lot of time. It cost us O of n. The main difference between arrays and linked lists is that in an array, an element or elements are indexed. So if I wanted to go to item at index 5, I can do that easily. In a linked list, you start at the head and traverse the list until you get to item 5, which is O of n. And this idea of traversal is the same as iteration that we did with arrays, where we go 0, 1, 2, 3, 4, 5. Except we like to call this traversal because you don't really know when the linked list will end. You start from the head and you keep going until you hit null. And as you'll see in our coding example, we're going to have to use something like a while loop when we implement our own linked lists because we don't usually know how long the list is going to be. Another advantage that an array might have is that most computers have caching systems that make reading from sequential memory, that is memory right next to each other, shelves right next to each other, faster than reading scattered addresses. And that's something that we've talked about already. Array items are always located right next to each other in computer memory. Linked lists and nodes instead are actually scattered all over memory, kind of like hash tables. So Iterating through a linked list or traversing through a linked list is usually quite a bit slower than iterating through items like an array, even though they're technically both O of n. However, these inserts that we can do in the middle of a linked list is a lot better than an array. What about hash tables? Remember this when we talked about hash tables? Well, just like hash tables, when we insert something into a linked list, we just scatter it all over memory and we can just keep adding it, keep adding it, keep adding it. And we don't have to do any of the unshifting or shifting on the indexes that we did with arrays, which is really, really nice. You can also delete nodes very easily versus with an array. But the one advantage that it has over hash tables is that there is some sort of order to linked list. Each node points to the next node, so you can have sorted data, unlike a hash table. So if we look at our big O of linked lists, we can see that prepend, which is a common language we say to add to the beginning of a linked list, prepend is O of 1. Append, which is at the end of the list to add a new item, is O of 1. Lookup, which we can also call traversal to look for an item, let's say we want to find 10, is O of n because we have to go from the head all the way until we find what we're looking for. Insert is also O of n because we have to go one by one, find the index. We don't know how long our linked list is. We find the index and then insert there, which technically could take O of n. And again, something that we're going to implement in code and have a better understanding of. And delete is also O of n because we have to find the items. Now, you're thinking to yourself, hold on, insert and delete in arrays are also O of n. So how is that better? And that's something that we're going to get into when we actually take a look at the code. Remember, this is the worst case, in which case we insert or delete the very last item. And most of the times, that won't be the case in linked lists. Again, something that we're going to talk about a little bit when we code our own linked list. But looking at a diagram like this, it's really hard to truly understand how they work and what linked lists are. So we're going to code our own. In the next video, we're going to talk about this final piece of the puzzle, what a pointer is, and then finally code our own linked list so we understand the big O implications a little bit better. I'll see you in that one. Bye-bye. Welcome back. Let's quickly talk about pointers, something that you'll hear a lot in computer science topics. A pointer is simply this. It's a reference to another place in memory, or another object, or another node. And in JavaScript, we can demonstrate it with something like this. If I have an object, let's call it object 1, that is a simple object that has A as true. And I'm going to comment this out. And now we do something like const object 2 equals object 1. We've just created a pointer, a reference to an object. And that is what a pointer is. It's simply a reference. Here, I'm not copying the object. I'm not saying object 1 equals A equals true and also creating another location in memory that says A equals true. In memory, when we look at our RAM, there is only one entry, A equals to true. And both object 1 and object 2 point to the same location in memory. To show you that is the case, let's just console log object 1 and then console.log object 2. And just so we're clear on this, I'm going to say 1 here, and this is going to be 2. So that if I run this, I have both A equals to true. But if I change object A, so accessing property A in object 1, and I say that is going to equal booyah, and I run this, look at that. Both object 1 and object 2 changed because I created a pointer here saying object 2 is going to reference object 1, like so. And they both point to the same location in memory. And that's what a pointer is. It's simply saying, hey, this is where it is in memory. And when we look at our linked list example, when we remove, let's say, a node at index of 2, and I hit go, 1, 2, we remove that. And that just disappears from memory. How does that work? Well, if we go back to our example, I can just delete object 1, And I'm going to change these into let because we are going to change the values here. If I click run, I get reference error. Object 1 is not defined at line 14. That's right over here. Okay, so let's just comment this out because object 1 doesn't exist anymore. If I click run, I still have object 2 as booyah, even though we deleted object 1. What's happening here? Well, the way it works in most programming languages is that our computers are going to delete the memory that is unused. And because it sees that object 2 is still referencing this location in memory, this value in memory, it's not going to delete it because there's still a pointer to this location in memory. And this is how things get deleted in languages like JavaScript. This is what you might call garbage collection, where as soon as we say object 2 dot, or object 2 equals hello now, and I click run, now object 2, which referenced the memory space that had a equals to true, is now just simply a string. So because JavaScript is garbage collected, that is, memory is managed automatically, this gets automatically garbage collected and deleted because nothing is pointing to it. However, there's low-level languages where you have to manage your own memory and you have to manually delete this unreferenced item in memory. And this can cause a lot of possible issues where you leave memory that's not being used in memory, which is a valuable resource. But then there's also benefits with non-garbage collected languages where you get to manage your own memory, so you can make things really, really fast and efficient. All right, I think that's enough for pointers. A pointer is simply a reference to something else in memory. And we're going to use this knowledge in our next video to create our very first linked list data structure. I'll see you in the next one. Bye-bye. Welcome back. It's time to create our very first linked list data structure. And let's say I wanted to create a linked list that has 10 pointing to 5, pointing to 16. A nice little simple one. First off, how would we go about visualizing this in a language like JavaScript that doesn't have linked lists? Well, we can simply say that we have a new linked list. Let's just use let here, my linked list. And this is going to equal to an object that has a head property. Remember, because the very first item in a linked list is the head. And we're going to have a node. The point of the node is to say, hey, anything can be in this node. Just put anything you want, and it's a container around this data. So think of node as a bucket of data. And in this case, we can just use an object to put our data in. All this node needs to have in a linked list is a value property of what the value of the node is, plus a next property, which is the pointer to the next node. Now, this value can be anything we want. And the next property has to be a pointer or a reference to the next node, in which case will be an object. So it'll be another object that we're going to reference in memory. This way, the value of the node can always change, but the pointers are always going to be pointing to that. So we can change items and nothing else will change. It will still point to that changed and updated value. Let me show you what I mean. We have the head here, in which case it's 10. So we want to set 10 as our value. And this head is going to point to the next node, which will have a value of 5. Make sure I add the commas in here. And the next value of what do you think? Well, the next node in the list, which is value of 16. And next, referencing what? Well, 16 is the tail of our linked list. So that means it has to point to null, or what we call null terminated. That means it's the end of the list. Perfect. So this is what we want to create, a linked list. Using this as our structure, we're going to create a class called class linked list. And this class, and we should be familiar with the syntax by now, will have a constructor, which is the function that gets run at the very beginning when we create the linked list. That's going to take a value. What does that mean? Well, when we finally say that we're creating a my linked list, remember, we want to create this. When I create my linked list, I'm going to instantiate the class, that is, run the class function here, run the constructor, and create the linked list. I'm going to say linked list, and then give it a value to start off the list because, well, the list can't be empty. It has to have something. It has to start with the head. So in our case, we want to start it with 10. And ideally, by running this command, we've created the first part of our linked list, just the 10. Let me comment this out since we won't need it for now. Now within this constructor, we have, well, the this.head reference because, well, we need to keep track of the head. And this head is going to simply have a value that equals to the value that we passed in, that is the 10 here. And then finally, the next. And what should the next be when we first create this list? Well, since 10 is the only thing that we'll have, or one node, next is going to equal null to begin with. Remember, constructor is all about creating the very first linked list node. What happens when we instantiate a class to start off my linked list? And then finally, we have two other pieces of information that we need to track. One is this.tail. And remember, the word this just refers to the linked list. So it's just referring to the linked list that we create. What is the tail going to be? Well, because we only have one item, the head is also the tail. So we simply say this.head. And by the way, I know this can get a little bit confusing. And as we go through this video series on linked lists, it is a bit hard to wrap your mind around. So I really recommend that you code along here and do the exercises because just watching me talk about linked lists is not going to solidify your information. It is hard to really visualize things. So you may need to build linked lists a couple of times to really get the hang of it. But this will become second nature once you get used to the syntax and also the idea of having this head and tail and referencing them. Anyway, the final piece of the puzzle is, if we want, we can keep track of the length of the linked list. This is optional, but I think it's good to keep track. And because we have one item, when we create this linked list, because we give it a value, we'll give it a length of 1. There we go. If I run this, I get an error because, well, I have this code that's not really JavaScript. So let's comment that out and click run again. I get undefined, well, because we haven't logged anything. But if I console.log my linked list and I run this, look at that. I have a linked list with a head that is value of 10. Next is null because, well, there's only one node. And a tail, which is the exact same thing, pointing to null, and a length of 1. Congratulations, we just built our very first linked list. However, it's time for a little bit of an exercise. Our list is not complete, right? We need to create this linked list. So we need to be able to add 5 and then 16. So my challenge to you is this. We want to create an append method. And this append method is going to take a value. And in here, we want to write a piece of code that allows us to say const or my linked list dot append and give it a value, if we look at our list, of 5 to append to our current list. So I want to be able to say append 5 and then append 16 to create our completed list of 10, 5, and 16. How would you go about doing that? And I'm going to leave this for you to try out. Remember, this may be a little bit hard, and I'll provide the solution video and we'll code along. But I do encourage you to challenge yourself and just think about what's happening and what we've done in the constructor to create this append method. Good luck, and I'll see you in the solution video. Bye-bye. Welcome back. How was the exercise? Were you able to figure out the append method? Let me show you what I would have done. The first thing we would want to do is to create a new node with the value. And we can do that quite easily, saying const new node. That's going to equal, well, an object with the properties that we should be familiar by now. We have value that is going to equal the value that we get as a parameter. And then the next, that will be null. So we have our new node here, and we want to attach it now after the 10 node, which is our very first node. Well, we can simply do that by saying this dot tail dot next, which is the, remember, this part over here, next equals null. So that is, what is the tail? That is the last item in our list, because this method doesn't know that we only have one item. We could have 100 items. We just want to add at the end. So it's going to grab the tail and then grab the next value of the tail. So it's going to grab the pointer of the tail and say, hey, instead of pointing it to null, point it to this new node that we just created. All right, we've pointed the tail to now point to the new node, which has next null already set up. And then we also want to say that this, what we had as tail before, which was the value of 10, is no longer the tail. We have a new last item. That is, this dot tail is now going to equal new node. And because we are running this operation after this one, when we run this, the tail dot next is still this node. And as soon as we update this node to have a next of the new node, we can now update the tail to be the new node. Because by that point, by the time this line runs, the next has been updated properly for this older tail value. And then finally, we want to make sure that we add the length to equal 2 now. So we're going to do plus plus. And just for fun, because we want to make sure that we do this right, we're going to return this, which is the linked list. Remember, this just references what this class is that gets instantiated. So we're just going to say return this so that we get back our linked list. I'm going to remove the console log for now and see what happens when we just run append 5. I'm going to click run. All right, I get returned our linked list, which has a head of value 10. Next is the new node that we created, the value of 5, and next null. And then the tail is value of 5, next is null. Perfect, with a length of 2. Awesome. It looks like it's working. Let's do this one as well. Append. And there we go. We have value of 5. So the head is referencing value of 10, which points to the next node, which has value of 5, which points to next, which is an object, that is the tail. Because of the way logging works, it won't show this nested. It'll just say that this is an object. But this is pointing to tail, which has a value of 16, next null, length of 3. How cool is that? We just created our linked list, our 10, 5, 16 linked list, just like that. I hope you got that right. But if you didn't, don't get discouraged. This takes some time to get used to. Luckily for you, once you write it a couple of times, then it becomes, like I said, second nature. So don't stress out, because I have another challenge for you. Now that you know how to do append, you should be able to do prepend, right? Prepend is adding to the beginning of the list. So let's say that in our list over here, we want to add 1 as our head now, instead of 10. How would we do that with a method called prepend? This prepend is going to take a value, and we're going to be able to run a command like my linked list dot prepend 1 to add the 1 at the beginning of this list. So code here, good luck. Let's see if you can solve this one, and I'll see you in the next video where I give you the solution. Bye-bye. Welcome back. Were you able to implement prepend? Let's have a look at what the code should look like. The very first thing we do, just like we did with append, is to create the node that we're going to add. So I'm going to say new node, value, and next. Now, next here, I'm going to leave as null. And I'll show you why in the next video that is the case, and we don't just have next equals to this dot head to reference the very first item in our list, which is 10. But for now, just trust me that this, we want to leave as null, because we can do that later. Right now, we're just creating an empty node with the value. Next, we want to say that our new node dot next, which is this value over here, is going to equal this dot head. So we've just created a pointer saying that the new node we just created is going to point to this dot head, the very first item in our list. Okay, that should make sense. And then obviously, just like we did with append, we want to update the reference now to say that this dot head is no longer equal to this old value. It's now the new node. And then finally, we want to add this dot length and make sure we increase the length of our list. Finally, if we return this, our linked list, we can say run. And look at that. We've prepended 1 to the very first item on the list, the head, and that is now referencing 10. And the tail of our list is now 16. That wasn't too bad, was it? In the next video, I want to talk quickly about this new node code that we're repeating, both in append and prepend, and what we might want to do with it. I'll see you in that one. Bye-bye. Welcome back. In the previous video, we talked about how new node over here gets repeated, both times in append and prepend. And as we create more methods on our linked list, we're going to have to constantly say new node, value equals value, next null. And usually we want to keep things dry. That is, do not repeat yourself in code. In many implementations of linked list, you'll see something like this, where new node is actually another class. For example, I can create a new class here, and this is how object-oriented programming usually works. We have classes that interact with other classes to create our programs. So you'll see a lot of implementations of linked lists that have class of node, and this node is going to have a constructor that takes a value, and this value will have this dot value equals to value. It's going to have this dot next equal to null, just like that. So that way, instead of us saying constant new node and creating this new node every time, I can just say every time that I want to create a new node, we can say let or const new node equals to new node and then the value. So every time we have a new node, we just instantiate what we call create and run this new node class that creates a node for us with a value property and a next property. So you might prefer using this syntax, but because I find this can get a little bit confusing, especially if you're not used to classes, I'm going to just keep things the way they are because, well, I think it's easier to read. And as you saw, it's fairly easy to implement if you want to do that on your own. Okay, just a quick segue. Let's get back to finishing our linked list in the next video. Bye-bye. Welcome back. We've just implemented prepend and append, and it should be clear to you why that is an O1 operation for both of these. We didn't really have to loop through anything. We just had a reference to the tail and the head, and we reassigned some values. Nice and easy. But now comes the hard part. What about these ones? What about lookups, traversals, inserts, deletes? I think we should code those as well to fully understand how linked lists work. This exercise is going to be a little bit tougher, but I'm going to give you a heads up that there's going to be some looping involved. We want to create an insert method. And this insert method is going to have an index and a value parameter, because we're going to want to be able to say insert at this location, this value into the list. For example, if I wanted to say my linked list dot insert, and let's say I wanted to insert at index of 2 the value 99, well, that would mean that if we go back to our example, index of 2 would mean 0, 1, 2. Right here, I want to insert 99 and have that point to 5. How would we go about doing that? I want to warn you, this can get a little tricky. And the best way to really think about it is to grab a piece of paper and a pen and draw out the steps that you should do. A good way to practice this and make sure you get it right is to use the Visual Algo website. and practice inserting and see what happens when you do index of 2, let's say 99. I hit go. See what happens here. You're going to have to code that action. Did you get that? Play around with this as you try and code the insert function. Like I said, a little hint that there's going to be some looping involved. You saw that in the demonstration or in the animation, there was some sort of traversal. So we're going to have to do some sort of traversal to find the index. And I also just want to code a quick print list function so that instead of using this way of printing our list, which as it gets deeper and deeper, gets harder and harder to understand, I'm going to just create a print list function that you should have access to make sure that your insert method is working. And this print list is simply going to just list our linked list, but instead of having this ugly printout, I'm just going to print it out in an array. So this is just going to be printed out in an array. All we're going to do is say const array, and this is going to be an empty array. We'll have a current node variable that will have this.head, so the first item in the list. And all we're going to do is do a while loop. Remember, this is similar to a for loop. We're looping, but instead we're saying while this is happening, while a condition is happening, run the below commands. So I'm going to say while current node doesn't equal to null, as long as there is a current node and we're not pointing to a null terminator. In that case, just simply add to the array.push, the current node value. That's it. We don't care about the pointers or anything. We just want to push to the array the value. And we want to then update the current node to equal current node.next. So we're going to keep going until the current node is going to be null, at which case we're going to stop. Again, while loops are really, really good if we don't really know the length of our linked list or we just want to do something while a condition is met. So we can just simply return the array here. Let's see how that would work. If I do, and I'm going to comment out the insert here because we're not going to do that yet. I'm going to just say my linked list dot print list. If I run this, there's our list. So using the print list command to check your work, see if you can create this method. Good luck, and I'll see you in the solution video. Welcome back. Let's see how we can implement the insert method. And this was a tough one, so hopefully you got it. If not, at least you tried so that we can see how we want to implement the insert method properly. The very first thing I want to do is, well, first of all, check my parameters. And this is something that you usually want to do with all methods. I know we simplified things, and when we looked at prepend and append, we never checked whether the value was something that we wanted. But when it comes to inserting something, we want to make sure, especially that the index is a value that we understand, so our program doesn't give any errors. And there's many things that we can do for a check, and I'll leave it up to you to really implement really good checking. But the one important check that I think we should have is if index is greater than or equal to this dot length. So if I give an insert of, let's say, index at 200 and our list is only 3 items long, I want to be able to handle that properly. In this case, I'm saying as long as the index is greater or equal to this dot length, in that case, just add it to the end of the list. So if I say insert 200, value of 99, I'm just going to add the 99 to the end of the list. And you can implement different variations of this. Maybe you can return an error if you want. But to simplify things, I think this is good enough. And we can just say return this.append, which we already have. We have to say this.append because we're referencing a method in this class. So let's say this.append. And we'll just add the value. There we go. So if I do 299 over here, let's add the print list at the bottom here. And if I click run, I get 99 added to the end of the list. But what if index was 2? Well, this now is the hard part. We want to first create the new node. And remember, we can create a new class instance if we wanted to. But in our case, we'll just create a new object that has a value of value and next of null. Nothing new here. We've seen this before. Here comes the tricky part. And I like to comment this out, or at least visualize it so we understand what we're doing. We have two nodes that are connected. And then we have a new node that comes along and says, hey, I want you to insert me right in between here. What should the steps be? Well, the first thing we need to do is to actually figure out which node the first one is. Because remember, to insert something, we can pick whatever index we want. So if we want to insert an index of 2, we want to grab whatever is at index of 2. So we need to traverse our list and say 0, 1, 2 to find this node and get a reference to it. Otherwise, we don't really have a reference to it. Remember, a linked list only has reference to this head and this tail. So the very first thing we want to do is to actually get to that node. And we're going to call this first node the leader, because that's going to be the first node that we're going to connect this new node to. And this new node is now going to point next to the old node, or the node that was initially connected to the first node. So I'm going to say that this leader node is going to be, well, how can we get that? We need to somehow traverse one by one until we find the index we're looking for. And to keep the code clean, I'm going to create a new method. I'm going to say this dot traverse to index is going to be a new method that's simply going to get the index that is 0, 1, 2, and I want to grab the leader. So if I want to insert the number 99 in here, I have to make sure that 10 points to 99 and 99 points to 5. So that means I need to grab the index, not here, and point it to the leader, that is the 10, the leader that we want of the list. So all I'm going to do is -1. So point to the leader, and this traverse to index, well, we're going to have to create it. And I have the this keyword here because, again, it's a method onto this class. I'm going to say traverse to index, that's going to get an index, and this is where we do our traversal, or looping. You might want to check for parameters here and make sure that it's a valid index. And that's something that you can do on your own. It's not very important for this example. We can assume that the index is going to be a valid number, a valid index. And in here, we're going to first have to do something like a counter. That's going to equal to 0. And we're going to say that the current node, and this is something we did similar to the print list. We're going to keep the current node as this dot head. And while the current, or while the counter doesn't equal the index, because we're saying keep traversing, go from the beginning, from the head, all the way until the counter is equal to the index. So keep going through the while loop as long as the counter doesn't equal the index. But as soon as the counter becomes the index, so while we reach the point that we want, in our case, traverse to index -1, that means as soon as we get to 10, then stop. But until then, I want you to traverse through this. So current node is going to equal current node dot next. So we're going to keep moving the current node over to the right, and we're going to increment the counter one by one. That's it. That's our traversal. All we need to do at the end, because we want to return something from this method, is to return the current node. And there we have it. We say traverse to the index. In our case, if we do insert to 99, it's going to receive to 99 here. It's going to create the new node, and it's going to traverse to index. 2 minus 1 is 1, so it's going to say 0 and 1. And counter is going to equal index, so it's going to exit out of this loop, and it's going to return the current node, which is 10. We grabbed a reference to the leader. Congrats. But we're not done yet, right? Once we grab the reference to the leader, what do we do next? Well, the next thing is we want to make sure that we grab the next item in this original list. That is, we want to hold a pointer to number 5. Again, we don't want to break this list. We want to make sure that the connections are working properly and that 99 comes after 10 and after 99 comes 5. So the next step we want to do in our insert method is to what I call hold, or let's just call it holding pointer. I could probably name that better, but holding pointer is nice. And we'll say leader.next. Leader.next is 5. And this 5, we now have it referenced in this variable that we'll have temporarily. Next, because we have 5 saved to this variable, referenced in this variable, we can now update the leader.next to point to our new node. So I can say leader.next is going to now point to new node. And remember, because of how references work, we've deleted the reference of 5 here. So 10 no longer points to 5, but we've saved the reference to it in here, in this variable. So right now, if we go back to our example here, we've removed the reference to this, and now 10 points to this node. That's better spacing. There you go. Okay, what do we do next? Well, we now need this node, this new node, to point to this one, like this. And that's pretty simple, right? We simply say new node.next is going to equal the holding pointer, the 5 that we are keeping in memory. And then finally, we say this.length plus plus because we've added to the list. And we can return this, or just so we know we did it properly, I'm going to say this.print list. Once we insert something, we're going to just print the list. Let's see if that works. I'm going to remove this so the code works and we don't need the print list. Let's run this command. Hey, look at that. So before we had this list, and let's actually print list here so we can see it. My print or my linked list dot print list. This is what we had before, and we added 99 in here, just like that. And just to test it out one more time, if I do my linked list dot insert again, and this time we'll give it 20, which doesn't exist, index of 20, and add 88, that should be added to the end of the list. And because with this insert, when we do the if check, we're just adding the this.append, which isn't printing the list. Let's just add a print list at the bottom here to make sure that that is working. There you go. 88 at the end. Very, very nice. I know that was challenging, and insert is probably the toughest function to implement or method to implement in a linked list. But practice this a couple of times, really understand what each step is doing, draw it out if you need to. But congratulations, we just implemented an insert function into our linked list. And you might notice here that we had to traverse where we had a while loop. And this might make sense now, right? Why we had the insert as O of n? Because we had to loop through our list. And lookup, which can also be called traversal, was also O of n. That was our traverse to index, right? If we're looking for an item at index of 10, for example, we'd have to look up. And the worst case is that we had to go through the entire list. Same with insert. All right, now that we've done the insert, you should be able to do the next one on your own. That is delete. Using something very similar to what we did with insert, let's add a delete, or I like to call this remove. Let's have a remove that has the parameter index of what you want to remove. Good luck coding this, and I'll see you in the solution video. Bye-bye. Welcome back. How did it go with the remove method? It should be fairly easy since we got the insert method, right? All we need to do is first check the parameters, and we might want to check whether the index is a positive number, whether the index is higher than the length, but that's something we've already talked about. So let's get to the meat and potatoes, the main part of remove. All we need to do is once again, get the reference to our leader. So that is, if we want to remove, let's say 99, so that is index of 0, 1, 2. In that case, we want to make sure that we remove the 10 to 99 pointer and instead point 10 to 5. And because of how memory works in garbage collected languages like JavaScript, as soon as we remove that reference, 99 is going to get deleted. So all we're saying now is remove this pointer and then just update this to point to this list, and this gets deleted. I hope that my little diagram there makes sense. Let's code this out. Well, we first find the leader, just like we did in our insert function, by using this dot traverse to index. So I'm going to say this dot traverse to index, index -1, and we have the leader. Now, we have the leader, and we can point 10 to now point to 5, but we need a reference to this 5. And the way we get that reference is to say const unwanted node, that is the node we want to delete, is going to have leader.next. That is, the unwanted node is going to equal leader.next, which is 99. And we got that variable, so we can do leader.next to equal unwanted node dot next. So we grab the leader, and then we said, this node that I want to grab it here by using leader.next, and then make sure that we get the pointer, that is 99 to 5, which is unwanted node.next, which equals to 5, the 5 node, to now be pointed from leader.next. And of course, so we don't forget, we have to decrease the length because we're removing a node by doing -. And we can just return this dot print list here. That wasn't too bad, was it? Let's go down here and make sure this works. I'm going to say that we want to my linked list dot remove at index of 2. So let's remove the 99. I'm going to run this. Look at that. We've removed 99. If I run remove again at index of 2, that is to remove 5. Oh, not print list, remove. And we click run, 5 gets deleted. Very, very cool. And once again, we know why delete is an operation of O of n, because we have to traverse to index. And going back here, we now have a better understanding of how this diagram works. If I remove the tail, we have to traverse through everything, one by one, until we hit the tail, and then just remove it, and there we have it. And I encourage you to play around with this animation a little bit more, having our linked list implemented. There are other methods that we can add to it, but these are the main ones of linked list that you can see. And this should give you a better idea of how we calculate big O notation with linked lists and where some of the drawbacks are. I mean, you can explain data structures for a long time, but without actually coding it yourself, it's hard to see why some operations take longer than others. And linked lists are very popular in interview questions. And now you have the tools to build your own linked list in a language that doesn't even have it natively, like JavaScript. Well done getting this far. In the next video, we're going to introduce you to the second type of linked list that I mentioned at the beginning. Up until now, we've created singly linked lists. But there's also a doubly linked list. What does that mean? For that, I'll see you in the next video. Bye-bye. Welcome back. Up until this point, we talked about singly linked lists, and we should have a good idea of how they work. But what is a doubly linked list? Doubly linked list is similar, except that it links to the node before it. Let's have a look at a little animation here. We have a head node. Let's say we just have one node. You see that we have an extra block here. We're not really sure what this does yet. Now, if we wanted to add a new block to this list, a doubly linked list, and we wanted to add a node that contains the value 10, well, we would now have a pointer to the next node. We'd also have a pointer, this is the new part, to the previous node, and the new node is going to point to null. And this now becomes the tail. If we added another node, well, we'd have the 10 node point to the new node. We'd also have the new node point to the previous node. And then finally, that becomes a tail, which means it points to null. And that's what a doubly linked list is. It has an extra little block here, an extra piece of data that also links to the previous node. Now, why do you think that's important? Doubly linked lists allow us to traverse our list backwards. So up until now, we were only able to go from the beginning all the way to the end. With a doubly linked list, I can start from the end and go backwards. In a singly linked list, there is no way for me to know what comes before 10, what comes before this node. In a doubly linked list, that is no problem. It's exactly the same as a singly linked list, but contains this additional pointer to the previous node. And searching through a doubly linked list can actually be a little bit more efficient. And lookup can technically be O of n divided by 2, because we can start at both ends, and if we know in which half of the list what we're looking for is, we can pick the optimum place to start. Now, the lookup here is still O of n, because if you remember, with our rule book with O of n divided by 2 is still O of n. But it's still technically a little bit faster. Now, the downside to a doubly linked list, as you can see, is that we might have to hold a little bit more memory, an additional block of memory. And we have a video talking about when to use doubly linked list and a singly linked list later on. But to understand this properly, I think we should convert our singly linked list that we created in the previous videos to a doubly linked list. So let's go have a look at how to do that. I'll see you in the next one. Bye-bye. Welcome back. We have our original linked list, and we just found out that our linked list is actually a singly linked list. But we want to convert this now into a doubly linked list so that we add that extra feature of an extra pointer. How would we go about doing that? Well, let's go line by line. And luckily for us, it's not that difficult. As you can imagine, if we go line by line and go into the constructor, the one extra piece of information that we need to add now is that we also have a previous pointer now. And this previous pointer will be null to begin with. So the head is going to point to null. And everything else stays the same. But what happens when we append something? Well, once again, we're going to add a new node that also has previous property, a new property that points to null. And we're still going to have the tail.next equal to the new node. And this doesn't change. But the only line that changes is that we need to add a previous property, because remember, append is adding at the end of the list. We want to add the previous property to equal whatever was at the end of the original list before we did the append. So all we would need to do is say new node dot previous is going to equal this dot tail, the very last item, before it gets updated over here to the new node. Let's see if append works the way we have it. I'm going to scroll down here and just comment out all of this code except for the first two lines, append 5 and append 16. If I click run here, I get a doubly linked list that has a head of value 10, okay? That points to next, which is the next node. We see value 5. That points to an object that we don't really know yet. And also points to a previous object. And within this 10 node, we see that previous points to null because there's nothing before the head. If we look at the tail, we see that the tail now has a value of 16. Next is null because it is the tail, it's the end. But the previous node is also pointing to this node 5. And the doubly linked list has a length of 3. Very cool. So all we've added is this previous reference. Let's do the same for prepend, that is to add at the beginning of the list. If we scroll up to prepend, we once again want to add a new property, which will be the previous. That will equal to null for now. And we want to keep everything the same. We want to make sure that the new node.next is going to point to whatever the head is currently. But we also want to say that this.head.previous, the previous should now point to our new node because it's no longer the head. And then we can update the head to be our new node, and this.length is going to increase, and we're going to return this. If I click run here, remember we're prepending 1, so we're adding 1 to the beginning of the list. We see that our doubly linked list now has a head with the 1 value. That's pointing to the next value, which is the 10. And our tail is still the same. Tail is 16. That points to the value of 5. So if we print list here, again, 1, 10, 5, 16, as we expected. What about the insert? How would that work? If we go to insert method here and go line by line, this first part, everything's okay. We have a new node, so again, we'll add a previous property that will be null for now. We're still grabbing the leader and traversing to the index. But now we have to do things a bit differently. We need to grab the leader as well as the follower. So if we wanted to add 99 here, we need to grab a reference to 10, the leader, and also the follower, 5. So I'm going to change the name of leader.next, that is 5 over here, to say follower. So the leader of our new node and the follower of our new node. Now follower is now going to be the 5. We're going to update leader.next, so that is 5, or leader.next, which is what comes after 10, to be the new node, our 99. And then new node.next is going to equal the follower, that is 5. But we also want to make sure that our new node dot previous is going to equal the leader, that is the 10. And also make sure that the follower, that is the 5, has a previous value that points to our new node. So if I print list here with our insert, I've inserted the value, but just to check that everything is working, I'm going to console.log this, which is our linked list. If I click run, I see that our linked list has a length of 5, and I'm going to change this to index of 1 so we can see it in our output here. I'm going to say index of 1. If I click run, I see that head is now value of 1. The next in the item is value of 99, as we expected, and it has both next and previous properties. And that's not too bad, right? As long as you visualize the steps and draw your diagrams, all we're doing is saying add the new node, or get the leader to point to the new node. The new node should now point to the leader, and the new node should point after it next to the follower, and the follower is now going to point back to the new node. You might have to go through this in your head or draw it out on a paper, but it should make sense now. And at the end of the day, singly linked lists and doubly linked lists aren't that different. As you see, all we're doing is just managing another pointer that points to the previous node. I'm going to leave the remove linked list up to you to implement your own in the doubly linked list, as you've learned up until now. It shouldn't be very different from what we did in the insert. But I hope you have an understanding of how linked lists work now. Interviewers love asking questions about linked lists because it requires a lot of information to be held in your head. And as you can see, they can be really complicated if you're not the type of person that thinks clearly through their steps and understand what they're doing one by one. And the steps are really important. That's why interviewers love this question, because they really get to see how you think. And with linked lists, as long as you draw out what you're doing step by step, it becomes really, really easy as long as you don't just start coding it out from memory. Just draw out the steps, think about your steps, and the interviewer will be impressed. I'll see you in the next one. Bye-bye. Welcome back. We've learned about singly and doubly linked lists. So let's talk about when you should use one over the other. Let's start with the singly linked list. The pro of a singly linked list is that it's a fairly simple implementation, especially compared to the doubly one. It requires lesser memory, as we can see here, less block. And because there's less memory when we do things like delete and insert, because there is technically less operation, we don't have to move around the previous property, it's a little bit faster. Now, the downside with a singly linked list is that it cannot be iterated in reverse or traverse from back to front. If we ever lose the reference to this .head node of the list can actually be lost in memory forever. So singly list is appropriate to use when you have less memory or memory is really expensive and you want to be careful of how much you use. And your main goal is that you want to do fast insertion and deletion. And you don't really have that much searching, especially when you have insertion at the beginning of a list. A doubly linked list, well, the good side of it is that it can be iterated or traversed both from the front or from the back. Another beauty is that if you need to delete a previous node, you don't need to traverse from the head node and find what the previous node is, which a singly linked list has no concept of. You can do that fairly easily with a doubly linked list. Now, the downside is that it is fairly complex, as we saw, to implement, and it requires more memory and storage because of this extra property. And there are some extra operations that we need to perform to make sure that when we do insert and delete, that the previous property is updated as well. So doubly linked lists are really good when you don't have that much limitation on memory, and when you want good operation for searching for elements, such as searching backwards instead of just forwards. Most of the time in interview situations, you're going to see singly linked list. You may be asked a theoretical or broad question about the difference between singly and doubly linked list, but most of the time, this is what you're going to see. All right, I'll see you in the next video. Bye-bye. Welcome back. I have a fun little exercise for you. And I know I call every single exercise fun, but I think this one is especially fun. Now, one of the most popular interview questions when it comes to linked lists is to reverse a linked list. What do I mean by that? Well, an interviewer is going to say, we have a linked list here. How would you go about reversing this list? If I have a list over here that is 1, 10, 16, 18, how can you make the linked list, go from 88 to 16 to 10 to 1? How would you reverse it and flip it? And we're going to use a singly linked list for this exercise. And all we want to do is create a new method that is going to say reverse. And this method in here will have to do some magic that will reverse this for us. Remember, we're not just printing out an array. We want a reversed linked list that now has 88 referencing 16, that has referencing or pointing to 10, and 10 pointing to 1, and 1 pointing to null. How would you go about doing this? Good luck with this exercise, and I'll see you in the solution video. Bye-bye. Welcome back. We have our list over here, and we want to be able to run my linked list.reverse that will reverse this list for us. Let's figure out the code here. The first thing we want to do is to do a bit of a check. Imagine if we only had one item in the list. If there's one node or item in the list, then, well, we don't need to really reverse it. It's already there. So if this list only contained one, just return whatever we have for now. So let's do that check here. And we can just say if this.head.next, and this exclamation mark means doesn't exist. That means if this head.next, if one is only one and it's null, this exclamation mark is going to turn this into the opposite, which the way JavaScript works will turn this into true. I know it's a little bit confusing, but hopefully you're with me on that one. All we're saying is if this is the only node and there's only a head node here, I could also do this by checking the length, and we have the length property. So I could do something like if this.length is equal to 1, but let's just keep it the way it is for now. If there is only one element, just simply return this.head, the node, or we can just return this as well. Otherwise, let's get into the fun coding part. The first thing we want to do is say we want to have the first item equals to this.head. And we're just keeping track of it here. So we're going to say that we now have a reference to this.head. And we also have a reference now to the second item in the list. So this is going to be first.next. So now that we have first and second, we can do some looping. We can say while the second node exists, that is, as long as second is not null. So as long as that's happening, we're going to create a temporary variable that holds second.next. So we can actually call this third if we want, but I'm choosing temp because this is going to change. So we have a reference to first, second, and third. So 1, 10, and 16. From here, we can now say second.next is going to equal the first element. First is going to equal the second element. And second is going to equal the temp element. Oh boy, what just happened here? I know that was a lot of code without a lot of explanation. But let's go through it line by line. We're looping here after we've grabbed 1 and we've grabbed 10. And now I'm going to say, as long as this second variable has a value and it's not null, if that node exists, then I want you to create a temp variable that holds 16. From there, I'm going to grab that second.next, which is the property inside of 10. And I'm going to say that 10 is now going to point, so second.next is going to point to the first. So 10 has an arrow pointing to 1. And the first variable, which was the head, now becomes 10. And the second item becomes 16. We've switched the pointers 1 to 10, now goes 10 to 1. And we've switched the variables, first and second, to now have 10 and 16. And we loop through and do the same thing, where we have the pointer 10 to 16 reversed, so that 16 points to 10. And we change the variable so that it's 16 and 18. So we loop through this, we loop through this, we loop through this. And then the final thing we need to do is to say that this dot head, because this dot head still has the value of 1 in it, we're going to say that dot next is going to equal to null. We're going to have 1 point to null. And this dot head now is instead going to be the first. And remember, by the time we loop through everything, first becomes 88 and second becomes null. So we are now changing at the very end 88 to be equal to the head. And we also want to make sure that the tail is now 1. And the way we do that, we have to go before the while loop and see here that this dot head, this first item, should be the tail now. So at the beginning, before we do the loop, the tail become this dot head. Right. I know that was confusing, but let's see if that works. This is one of those problems that you really have to draw it out. And just by looking at this code, it's really hard for you to understand what's going on. I recommend that you code this along and step by step, perhaps console log to understand what's going on. If I reverse this list and click run, I get undefined because we have to return something. So let's return this dot print list. I'm going to run this. All right, let me just make sure that we're reversing. I'm going to comment it out. So we have the original list, 1, 10, 16, 88. If we reverse it, we have 88, 16, 10, and 1. And just for good measure, instead of printing list, let's just return this here. So we get the entire linked list to make sure everything is working properly. I have a linked list that has a head value of 88 and a tail value of 1. Looks like it's working. Awesome. Good job getting this far. And if you're able to understand this, I think this is probably the most difficult concept to understand in this entire course. So if you're able to get this, good job. If not, you might have to watch this video a couple of times. In the end, and this is the beauty of programming, all we're doing is logical steps. And no matter what language you use, whether it's JavaScript, like we did in this case, the steps to create a linked list are the exact same. Syntax may differ, but the logic is the same. I'll see you in the next one. Bye-bye. Welcome back. In this section, we learned all about linked lists. We learned how it doesn't come pre-built in a lot of languages, such as JavaScript, but it does in others. That is because linked lists are low-level data structures. It's used a lot actually in other data structures like hash tables, and as we will see in some of the upcoming ones, such as stacks and queues that we're going to talk about. It is a fundamental data structure that is very, very useful in computer science, and also a very popular question when it comes to interviewing. We learned that when it comes to linked lists, there's no random access, in the sense that when looking for something, you have to actually traverse the list. With hash tables, we can find things right away. With arrays, we can find things through indexes. We have slow lookups. We have to traverse through the list if we're searching for something. However, they are ordered, unlike hash tables, and linked lists allow us to have this sort of order. If we had a large number of items in an array, and we keep adding to that array, we'd have to have excessive overhead costs copying the array in memory and doubling up the space when it reaches the limit to create a larger array. Versus a linked list where we can have a fast insertion and fast deletion, especially once we have a reference to where we want to insert or delete that node. This also becomes really, really fast when it's at the beginning of a list or the end of the list. And we're going to see that coming up when we talk about stacks and queues. The primary reason to choose a linked list over something like an array is simplicity and ability to grow and shrink as needed. Now, working with them, as we saw, can be a little bit weird and difficult to just manage all the pointers in your head, but they are pretty lightweight and self-contained in that they can be quite flexible as well. That's why you're going to see linked lists in a lot of places, like implementing file systems on your computer, or even browser history, right? When you go back and forth on a browser, you can think of that as a linked list because you can traverse one by one from one place to another. And remember with our hash tables, how we had this issue of collision. And when we had a collision, we had to do something like this, where we combined John Smith and Sander D into two nodes, and the first node pointed to the second node. If we go back to our hash table data structure that we created, if we scroll down to the set method, where we set a key and a value in the hash table, we did a check here to check if this address exists, and then afterwards, we used an array to push our items in case we had multiple items when we had a collision, because sometimes we can set our hash table memory size to be a lot smaller, like 2. And you might be able to see why now, instead of using an array, which every time we need to insert a new item, I mean, it works because we're pushing to the end, but if we had to delete an item on the hash table, we'd have to unshift the array, which, as you know, is very slow. So we can modify this now to something like a linked list so that a delete becomes a lot easier than if it was an array. And that's something that I'll leave up to you. But you should have a good sense of why these data structures exist now and why you might want to use a linked list over an array. We also added another piece of the puzzle in our mind map. We've talked about arrays, about hash tables, and now we talked about, if you see over here, linked lists. Our singly and doubly linked lists with their big O notation. And just a hint here, as you can see, linked lists are related to something we're going to talk about coming up. That is trees and graphs. But at the end of the day, we've just managed to add another data structure to our tool belt as engineers. Congratulations, and let's learn about more data structures in the next video. Bye-bye.